Hi, today I will show you a problem that is solved by people in a very complicated way, but that is very easy to solve if you know your ratio. So the ratio thing is just a way to represent a proportion. And for example, if I write something like, yeah, not like this, but if I write 1.2, that means that if I have 1 of something, I have 2 of something else. If I write, for example, 2, 3, that means that if I have 2 of something, I have 3 of the other things. And what's nice with that notation is that it can be represented by many fractions. We can say 2 over 5, which is mostly how people represent this ratio. We can also say 3 over 5. We are just interested by this relatively to the whole. We can also say 2 over 3, which is simply compared one part size to the size of the other part. So that's very powerful. And obviously, if you do something like this, then you can represent 6 different fractions, but even more because you can pick this one compared to this one compared to the sum of the other, this one compared to the sum of the two other, and then this one compared to the whole, this one compared to the whole, this one compared to the whole. So that makes already 6 different fractions you can work out, and then all the inner fractions. So ratios are very, very powerful, more powerful than a fraction. So I will use this notation because it makes things easy. So what we see there is a diagram where this line is parallel to this line and to this line. So these 3 lines are parallel. When you see that, you think Thales because you have lines that are secant and parallel lines, so it screams Thales. But what you can also think of is similar triangles, which is another way to say Thales. And you can prove that these 2 triangles are similar in an easy way. If 2 of the angles have the same amplitude, then the third angle will have to match, because in a triangle, if you know 2 angles, you can determine the third. So this one is the same as this one because they are opposite and they share the same side. This one and this one, they are also of the same amplitude because now these two, they are internal angles with relatively to the parallel. I don't remember how we say that in English. And because we show these angles are the same, then we can say that this one have to be also of the same amplitude, or we can reuse the same arguments with the parallel line if we want. But what we achieved here is to say these 2 triangles are similar. That means one is a scaled version of the other. And that's all we need to solve this. And to continue, I don't know what I did set up that. Okay, if I take this line, it has some length I don't know. I could say, okay, no, I will not say, okay, something. I will draw the other one, and we have this line. And if we see these 2 lines, they are the same as this line because they are parallel, so they have the same length. And there I have 6, there I have 4, and I can note that as a ratio, and that would be 2, 3. So that's the ratio I use as an example here. These 2 segments, they are in a ratio 2, 3. That means that if I write in terms of ratio, so I'm not writing length, I'm writing weight in the ratio. This has a weight of 2, and this has a weight of 3. That means that if this measures 2 inch, this one would be 3 inch. If it's 4 inch, this one would be 6 inch. That's all it says. I don't know the length. I just know it's 2 something would be worth of 3 something in the other side, and that's all I care. And because we know that they are all in the same kind of ratio, the same here, this one is 4, so this one is 6, I can find this length and this length, because this triangle, it has this side that has a weight of 2. So what would be the weight here? Then to know that, I will take 6, and if I take 6, is the equivalent of taking this whole line in my ratio, which is 5. So I want to divide by 5, and that would give me something, and then multiply by 2, because to go from 5 to 2, I need to divide 5 by 5 first, and then multiply by 2. So I obtain this ratio, this coefficient. So all I have to do now is apply it to 6. So 6 divided by 5 is 1.2, times 2 is 1.4. And there I will write it as a length. So here we have, so I said 6 divided 6 divided by 5, 1.2, 2.4. So that would be 2.4. And I can check, I can take now this 4 over there, and I say, okay, I want to go from all of this, which is 5, so I will have to divide by 5, to 3, so I will have to multiply by 3, and if I do that, 4 divided by 5 is 0.8, 0.8 times 3 is 2.5. So we have the same result, which is normal because we use the same ratio. Obviously, I made it more complex in the explanation that it has to be, to explain a bit what this notation means and what are the advantages of it. But when you know that the ratio, the viewpoint of you solving the problem is literally, oh, I have a 6 and 4, and I can simplify. So it's 2, 3, okay, and I want to go to 2, so I divide by 5, and I multiply by 2, and you are done. There is no thinking in that, you are done. Because you quickly see the similar triangles, then you know, okay, it's just a scaling, so I have to scale the 8 to find the new 8, and when I have that coefficient, I can apply it to find the green line. So that's all there is. You don't have to put complex equation, just knows your ratio. Thank you for listening.